Okay, good morning. Today we will be solving some problems related with n-step transition probabilities. If you remember, last time we ended with a discussion of the two umbrella problem. Actually, we didn't really discuss it much. I posed you the problem. I have two umbrellas, and every morning as I walk from home to work, I pick an umbrella with me if it's raining. And I don't take an umbrella with me if it's not raining. In the evening, on the way back home from work, again, if I have an umbrella at my work location, I'm going to take it with me if it's raining, and I won't if it's not raining. Question is, if I start on day 0, at time 0, with one umbrella at each location, and given the probability of rain, what is the probability that at some point in time I'm left in the rain with no umbrella? Okay, so for this I ask you to think about the problem and find a Markov chain that models this situation. Any ideas? Sometimes when we are faced with a problem like this, one of the main difficulties is extracting the Markov chain and extracting the state space, because in this problem, in this example, once we define the Markov chain, the rest is going to be quite easy. Any ideas?
I tried, but
yes.
I focused the number of umbrellas, 0 to 1, and we start from the 1.
Very nice. So the 0 to 1 with the number of umbrellas where? At your current location?
Yes. I
very nice.
I start from the 1, and with probability P, if rain, we go to the place.
Right.
To the number of place that we have two umbrellas.
Very nice. What's your name, please?
Süleyman.
Süleyman. So what Süleyman is saying is, so let's call this the two umbrella problem. What Süleyman is saying is, let the state at time n be the number of umbrellas at my current location. Now, given that there is an umbrella in my current location, whether there will be one umbrella or two umbrellas at my next location is determined by whether or not it rains during my trip. So clearly, this is a Markov process. So what are the states then? As Süleyman also said, 0, 1, 2, right? So xn takes values in 0, 1, 2, and this is my state space. Any questions here? Okay, so let's draw the transition probabilities, one-step transition probabilities between these states. Let me see if there's a better marker. Okay, so from 0, okay, if I have no umbrellas in my current location, I really don't have a choice. Maybe, shall I order these states differently? 0 to 1 is perhaps better, because from 0, I cross to 2 with probability 1. Okay? From state 2, if it rains, I take an umbrella with me, and in my next location, there will be one umbrella, because originally there was 0 there. So from 2, I cross to 1 with probability P. P is the probability that it rains. P is the probability of rain. Okay. If it does not rain, I don't take an umbrella with me. So with probability 1 minus p, I go to state 0. If I'm in state 1, there is an umbrella at my location and another umbrella at the other location. Now, if it rains, I take my umbrella to that location. So what is the number of umbrellas in that location now? 2, right. So with probability p, the number of umbrellas in my next location is 2. What if it doesn't rain? You stay at state 1. So that is my Markov chain, very simple Markov chain for this problem. Now, the question that I wrote in the lecture notes for you to answer is the following. Given that x0 is 1, meaning I start with one umbrella at each location, find the probability that on my trip to work on day 2, I am left in the rain with no umbrella. How do you think we can compute this probability? Well, you could do various, there are various ways to reason about this, but we will employ our two-step transition probabilities. So first of all, let's remind ourselves, what are two steps? First of all, let's go from the main statement of the problem. Let's call this event, I am left in the rain with no umbrella on my trip to work on day 2. Suppose this is event A. The probability of event A is the probability that at the beginning of day 2, there is no umbrella in my location and it rains. So no umbrella at my location means that xn is 0. But what is n? The trip to work on day 2. So the first trip from home to work on day 1 is trip number 1. Trip number 2 is from work back to home on day 1. The trip to work on day 2 is trip number 3. But I'm interested in the state here, which is x2, right? So because x0 is here, x1 is the state here, so x2 is the state here, right? So this is the probability that x2 is equal to 0 and it rains. Any questions? All right. But I'm also given. So I need to compute the probability of A given that x0 is 1. Okay, so this is what is asked in the question. Right? So this is the probability that x2 equals 0 and it rains given that x0 is 1. Okay? But I can write this as the probability that it rains given x0 equals 1 times the probability that x2 equals 0 given x0 is 1. Clearly, the probability, the event of rain is independent of the state. As specified in the problem, this probability is always P. Okay? So, but what is this probability? This is what we have defined as P102. The probability of transitioning from state 1 to state 0 in 2 steps. Okay. Any questions? Okay. So, of course, we can find the probability of transitioning from state 1 to state 0 in 2 steps easily using the Chapman-Kolmogorov equations. But I want to compute the whole matrix of transition probabilities such that maybe using it we could answer questions about further trips. Okay. So, if you remember, the P2 matrix is the matrix of Pij2's, and you can compute it by multiplying the matrix P with itself. Okay? So, what are these entries? For the rest, to find a numerical answer, actually, let's let P equals 1/2. Let's compute this probability for P equals 1/2. So what are my entries in this matrix? From 0 back to 0, there's no transition. From 0 to 1, again, there's no transition. From 0 to 2, the probability is 1. From 1 to 0, there's no transition. From 1 to 2, 1 to 1, it's 1 minus p, which is 1/2. From 1 to 2, it's again 1/2. Okay? And from state 2, I go to 0 with probability 1/2. From 2, I go to state 1 with probability 1/2. Okay. So let's multiply out the matrix P with itself. 1/2. Right? This row and this column makes, again, 1/2. Oh, 0. Wait. The third one. This row and this column is 0. And I don't know why I drew another matrix here. Sorry about that. This row and this column, 1/4. This row and this column, 1/4, right? This row and this column is 1/2. This row and this column is 1/4. This row and this column, 0. This row and this column gives me 1/4. And this row and this column gives me 3/4, right? Okay, so these are the 2-step transition probabilities. Now, how do I use that to find the solution? So basically, it's P, which is the probability that it rains, multiplied by P102. What is P102 here? Let's look at the P2 matrix. P10. It's this entry. You're right. Okay. So the answer is 1/8. Any questions? what if the question asked me, find the probability that on my trip back home on day 2, I get in the rain with no umbrella?
Then we should use the third order of the...
Right, exactly.
Third.
3-step transition probabilities. Exactly. Okay. Any questions? What's your name, please? Atabak. Okay. So, let's do another example. If you remember, last time we had this example of the student Burak taking class 202, and we left it we left our discussion of that unfinished. So, let me sort of verbally say it, and then we can draw the Markov chain. Every time Burak takes the class 202, he is going to pass with probability 0.2. If he fails, he can either take it again. He will either take it again with take it again, or quit his major with equal probability. So, what is the underlying Markov chain? How many states are there? Ecem? 3 states. What are they? Taking 202. Having passed 202 and having quit. Okay. So let's number them, if you will, as 1, 2, 3, maybe, or taking 202. Let's have this state, passed 202, and quit. And I can number these 1, 2, 3 for convenience. From state 1, I go to state 2 with probability 0.2. From 1, I go back to 1, or to 3 with equal probability. So those should be 0.4 and 0.4. So let me draw my transition probability matrix. From 1 to 1, it's 0.4, 1 to 2, 0.2, 1 to 3, 0.3. Sorry, 0.2 again, 4 again. From 2, okay, what is the transition probability from 2 to 2? Back to itself is 1, right? How about this state? Again, same. It transitions back to itself with probability 1. So then we have 0, 1, 0, and 0, 0, 1. That is my transition probability matrix. So let's see what happens after 2 transitions. The question in the lecture notes asks us what happens, after several transitions, and in fact, it's asking us to infer what will happen eventually. All right, so let's compute p squared. 0.4, 0.2, 0.4, 0, 1, 0, 0, 0, 1, multiplied by the same thing. And here, easily, we get the first column, a row and the first column, that's 0.4 squared. If you will, let me just write 0.16. And then this and this gives me 0.08 plus 0.2, 0.28. This and this give me 0.16 plus 0.4, 0.56. This and this is easy, 0, 1, 0, 0, 0, 1. Okay. let's, do you see that as we repeat this multiplication, let's try P3 for example, we're going to multiply 0.4, 0.2, 0.4, 0, 1, 0, 0, 0, 1 with P2, which is 0.16, 0.28, 0.56, 0, 1, 0, 0, 0, 1. Now, if you do this multiplication clearly, you'll see that the second and the third rows do not change. Okay, the only change is in the first row. This element becomes 0.4 cubed. This element becomes something, this element becomes another thing. I will try to find a pattern actually. Let's name this. Let's name this A3 and let's name this B3. And let's try to find a pattern for A3 and B3. So, okay, Pn in general is Pn minus, it's P times Pn minus 1, right? So 0.4, 0.2, 0.4, 0, 1, 0, 0, 0, 1 multiplied by 0.4 to the n, which I clearly, n minus 1, which I clearly know from the pattern. And this is a n minus 1, b n minus 1, 0, 1, 0, 0, 0, 1. Okay. So now from here we see that when you do the multiplication, this is 0.4 to the n. How about this? 0.4 an minus 1 plus 0.2. Okay, 0.4 an minus 1 plus 0.2. And the other entry is 0.4 bn minus 1 plus 0.4. Okay. And let me write this side. It's 0.4 to the n, a n, b n. So what I find is that an is 0.4 an minus 1 plus 0.2. It's going in that way. Pn is that. So if, you know, it seems that if you did one more computation, it will seem like this value is converging to 0. In fact, it is, right? It's going like 0.4 to the n. But the others are converging to non-zero values. So if really convergence happened, what would those values be? Well, so basically if the p to the n matrix, as n is increased, goes to some p infinity matrix, then we would have this entry being equal to the its value in the previous iteration, right? So we would have a infinity, if you will, be equal to 0.4 a infinity plus 0.2. And b infinity would be 0.4 b infinity plus 0.4. Right? And this gives me a infinity is equal to 1 over 3 and b infinity equals 2 over 3. So it seems that eventually my matrix is going to converge to 0, 1/3, 2/3, 0, 1, 0, 0, 0, 1. What does that tell you? Let's call this p infinity. What does that tell you? It says that after a very long number of transitions, the probability of still being in state 1 goes to 0, and I'm twice as likely to be in this state as I am to be in that state. That does not send a happy message maybe, but sorry about that. Essentially it tells me that eventually only these two states will be occurring. Those are absorbing states, and next time we'll see, in fact, properly the classification of states in a Markov chain, where we'll define this properly. Okay. Any questions about this? Yes, please, Ismail.
In previous question, umbrella question, if we haven't given the day constraint for any day, are we going to use the same thing in this question? I mean, are we going to think the steady state condition?
We can think about the steady state. That's a very good question, actually. We can think about what steady state is going to look like in this example. At steady state, meaning after a long number of transitions, a large number of transitions, we do not have an absorbing state here. So we will be seeing all of these states with certain probabilities. And we will learn how to compute those probabilities when we study steady state probabilities in maybe 2 lectures time.
Türkçe sorumuzun yani 20. günde bizim umbrella şemsiyesiz olmamız ihtimalle herhangi bir günde şemsiyesiz olma ihtimalimiz aynı mı olacak?
At steady state, yes. At steady, so basically that's a very good question. Currently, when I compute the probability of switching, okay, when I compute the probability that x2 is 0, given x0 is 1, okay? This is the transition probability of going from one umbrella to the 0 umbrella state in 2 transitions. Now, of course, it matters that for this probability of being in the no umbrella state after 2 transitions, the past is important. The fact that I started with one umbrella at time 0 is important. However, if you think about it, after 50 transitions, the previous, the initial states may be less and less relevant. After 100 transitions, it may be even less relevant. So after a while, we will reach a steady state where essentially the probability of being in the 0 umbrella state does not depend on time. Right, and we will, I will precisely define this later on. Okay, so let's do another example. Remember, last time we introduced something called a random walk. So I'd like to address that again. And basically, again, to answer your question with writing the transition probabilities down, you asked about Pij, n as n goes to infinity, essentially, right? And under certain conditions, this will have a limit. Pij, and under other conditions, the limit will not depend on the initial state I. To sort of do a sneak preview of further lectures, we will have this convergence whenever there is no periodicity in the chain. And furthermore, if there is a single recurrent class, we will have the converged values being independent of the starting state. The two umbrella problem is an example where this holds. However, in this problem, well, this is kind of degenerate because there are too few states. But here we have more than one recurrent state. So if we start here, for example, we will always stay here. But if we start here, there's a possibility that we end up in state 1 or in state 2 or state 3. So anyway, we will discuss this convergence in upcoming lectures. So let's revisit the random walk. Okay. We are doing a random walk on the set of integers. Okay. And the probability of moving right or left are each equal to 1/3. We stay in place with probability 1/3. Given that x0 is 0, meaning the initial starting state is 0, compute the probability of the walk reaching the value 2 before ever hitting -2. Right. So we go right or left. So basically, this is state 0, 1, 2. I mean, what am I doing? -1, -2, 1, 2, 3, etc. And at every state, we either stay in this state, go to the right with probability 1/3, or go to the left with probability 1/3. Go to the right, go to the left with probability 1/3, etc. So I'm not drawing all of the values. Now, question is, given that I start in state 0, what is the probability I reach 2 before ever hitting -2? How do you think about this? I claim that anything beyond 2 is irrelevant to us. Once we reach 2, we're done, so problem is over. Anything beyond 2 is irrelevant. Similarly, anything beyond -2 is also irrelevant. So I'm claiming that we can modify this chain to find another Markov chain on which we can answer our question. And that modified Markov chain is obtained by truncating the Markov chain, but we need to fix these probabilities. The probability of going to 2 is 1/3, and the probability of crossing from 2 to 1 is 1/3. But once I'm or in the original chain, but in the modified chain, once I reach 2, game is over. So how should I modify? I should make state 2 an absorbing state. Right? Similarly, if I reach -2, I lost essentially. Because my goal was to reach 2 without touching -2. If I touch -2, again, game over. Okay, so these now become absorbing states in the modified Markov chain. Is that clear? If I solve this, I get the answer to my problem. Yes, it is a different Markov chain from the original Markov chain, original random walk. But in terms of answering my question at hand, this does the job. It is sufficient. Okay. Now, this is a little bit like this problem. we start here, and eventually we will either get absorbed in state 2 or we will get absorbed in state 3. And what happens is eventually these two outcomes share the probability. In this example, their shares are 1/3, 2/3, meaning this is twice as likely as the other. Okay. Now, what do you think in this case? What's your name, please?
Melis.
Melis.
Yeah, I think this should be a 5x5 matrix or something like that.
Yeah, right. Put it in a matrix, right?
First value we can write it then. We are starting from 0, so we need minimum 2-state matrix. We can calculate the probabilities maybe.
Or maybe I can do something by inspection. Yes, please.
Can we modify again the middle part as a one state maybe?
Why would you want to do that?
Because we are trying to reach either the
You could possibly do that, but it'll take more work than solving the problem directly. What's your name?
Ihsan.
Ihsan. Yeah. Yes, please.
I think the answer is 1/2 because the diagonal is symmetric. So
Right.
the way I'm trying to do it is like
Exactly. The situation is completely symmetric. So, right. Does everybody see what's your name? Mustafa. As Mustafa said, I'm starting in state 0. It's in the middle, and the situation is completely symmetric. I should be equally likely to go to 2 first as I am to go to -2 first. So what is the probability that I go to 2 before going to -2? In other words, in this chain, if I go to 2, I am absorbed, right? And so that sample path would be like 0, 0, -1, 0, for example, 1, 2, and then it is all 2s. Okay? That is the kind of sample path that will end in an infinite sequence of 2s. There's another kind of sample path that ends in -2 and will continue with forever with -2s. So among these two sample paths, which is most likely? Well, in this example, this was twice as likely as the other one, but here the situation was not symmetric. Here, by complete symmetry, I don't even need to write any equations. I can simply infer that the probability, desired probability is 1/2. But if the situation was not symmetric, and if you have looked for a systematic way of computing the absorption probability, well, there are various things you could do. You could do that, or you could write a set of equations. Let me try to do that. I'll have to be quick because we have one more problem if we can manage. Okay, so I would say let AI be the probability of reaching 2 before -2, given that I start at state I. Okay, I define the AI as the probability of reaching 2 before -1, given that I start in state I. Now, I'm trying to compute A0 in the question, and I found that A0 is a half. But then I can find A0 in terms of other things. Now, let's start by A2. What is A2? A2 is 1. Okay? What is A1? A1 is 1/3 A1 plus 1/3 A2, which is plus 1/3 A0. Because when I'm in this state, 1, with probability 1/3, I will be back in 1 transition. With probability 1/3, I will go to 2. So now I'm dealing with A2. With probability 1/3, I go to A0. So this we know is 1. Okay? So I have an equation, A1 equals 1/3, and maybe let me simplify already. 2/3 A1 is equal to 1/3 plus 1/3 A0. That gives me an equation. Another equation I can get using A0. A0 equals 1/3 A0 plus 1/3 A1 plus 1/3 A -1. Okay? And so this says 2/3 A0 equals 1/3 A1 plus 1/3 A -1. So I get another equation. And for A -1, I get another equation. For A, let me write that for completeness. A -1 equals 1/3 A -1 plus 1/3 A0 plus 1/3 A -2. But A -2 is 0. Right? So that's gone. So I have basically 3 equations in 3 unknowns. And solving those, I can find the result. Any questions? Yes, please, Ecem. Excuse me? A -2 is 0 because AI is defined as reaching 2 before reaching -1. So the next question, and we may not have time to finish it, is the question about doing a random walk on a finite set. So in this example, it's like the spider and fly problem, spider and insect problem on the finite windowsill. Truncate the random walk in the previous example. Now we really have 5 states. -2, -1, 0, 1, 2. And the probabilities are the same. With probability 1/3, we stay in place. With probability 1/3, we cross to the right. With probability 1/3, we cross to the left. But there are 2 endpoints. Okay. Now the question is, given x0 is 0, compute the expected number of transitions until the walk hits 2. Right. So what is the difference of this Markov chain from the the modified Markov chain I made up for this problem?
There is no absorption.
Very nice, Melis. No Melis, right? No absorbing state at all. So when I go to 2, I will still get out of 2, and if I go to -2, I can still go back and go to 2, etc. So this is a little bit like the 2 umbrella problem, where every state is visited again and again. There's no absorbing state. So such a question is then well defined. What is the expected number of transitions until I get to 2? Here, that question would not have been defined, because I may not ever get to 2. Right? Here, that question is defined. So how can I compute that expectation? Again, I'm going to define Ti as the expected number of transitions to reach state 2, given that I started in state I. Okay, then I can write a set of equations again. For example, what is T2? T2 is clearly 0. What is T1? T1 is, well, you have to make one transition first. And if that transition, so basically you make one transition. And with probability 1/3, that transition is back to 1. So the remaining number of transitions until you come back to 1 is T1 again. Go to 2 is T1 again. With probability 1/3, you make a transition into 0. So the remaining expected number of transitions to hit 2 is T0. With probability 1/3, you go to 2 directly, and that is T2, but that's 0. So that's equation number 1. Let's write another equation for 0. T0 equals, now you tell me maybe. One, right, plus 1/3 T1 plus 1/3 T0 plus 1/3 T-1. That's another equation. I can write an equation for T-1 similarly. T-1 equals 1 plus 1/3 T-1 plus 1/3 T0 plus 1/3 T-2. It gives me a third equation. I can write a fourth equation. T-2 equals 1 plus 2/3 T-2 plus 1/3 T-1. How many unknowns do I have? T-2, -1, 0, 1. Four unknowns, 4 equations. Should be okay to solve. And I believe I solved it, but I'm not sure whether I should give you the answer now. I'll leave this as exercise. Okay, solve this. And next time we will talk about the classification of states. I'll see you next time.